Having studied about the Laplace transform and various applications of it, we would like to start this video with a question related to the Laplace transform of derivative. Now, here we are obtaining the Laplace transform of cosine kt. Remember, we have already obtained the formula for it, but here we will be using the Laplace transform of derivative to obtain that. Now, if we choose f of t to be equal to cosine kt, then we'll have the double derivative, that is the second order derivative of f of t with respect to t, to be equal to minus of k squared f of t, because cosine will give you sine and the k comes out in the first derivative, and in the second derivative another k comes out, the sine changes to cosine, but in the meantime you also have a minus multiplied to it. Now the Laplace transform of the double derivative that we have, that is f double dash or the double prime of t, which is the second order derivative with respect to t, we have obtained that to be equal to minus k square can be kept outside, and then we have the Laplace transform of f of t, because that's what we get on the right hand side over here. Now from this what we get is, well, for the double derivative we have s squared, the Laplace transform of f of t, minus s times of f of 0 minus, this is the f prime 0, and we take it at obviously we are taking it at t is equal to 0. So this is the Laplace transform of the second order derivative, if you remember, on the left hand side, and on the right hand side we have minus of k squared times of the Laplace transform of f of t. Then on the left hand side we have s squared, and we can bring this right hand side term onto the left hand side, so we have s squared plus k squared, because that becomes positive, and that is multiplied to the Laplace transform of f of t. And at t is equal to 0, that is at f of 0 over here, since we have f of t to be equal to cosine kt, we have f of 0 is equal to cosine of 0, which is equal to 1. So this simply is minus s times of 1. And if we are taking the first derivative of f of t, then we are getting k times of sine t, k times of sine kt in negative form. But again, if we put t is equal to 0, we'll have this to be equal to 0. So this is going to end up with 0 for sure. And on the right hand side, since we have brought that term onto the left hand side and added over here, we have a 0 over there as well. So we have s square plus k square multiplied to the Laplace transform of f of t, and we take the s to the other side, and that gives us the Laplace transform of, remember what we had chosen for f of t, that was equal to the cosine kt function. So we have the Laplace transform of cosine kt to be equal to s over s squared plus k squared. Now this was obtained in a straightforward manner just by considering the Laplace transform, the formula for the Laplace transform by definition. But here we are obtaining that formula by using the idea of Laplace transform of derivative. So that's another way of doing it. Then in another bit we use the Laplace transform method to solve the differential equation, which is given by this, that is the second order derivative of x with respect to t plus omega naught squared x at t is equal to 0, and we are given the initial condition that x at 0, which at t is equal to 0, is equal to a, which is a constant. The first derivative of x at t is equal to 0 is 0, and we have omega naught squared to be equal to constant. Now for that we simply apply the Laplace operator to the equation. So what we have is the Laplace transform of the second order derivative of x with respect to t plus the Laplace transform of omega naught squared x as a function of t, and that is equal to 0 on the right hand side. On the left hand side, with the second order derivative, we have the following result, that is s squared times of the Laplace transform of x of t minus s times of x at 0, and then minus the derivative of x at 0, the first order, plus, well, the omega naught squared can come outside, so we take it outside and we have the Laplace transform of x of t, and on the right hand side we have 0. So now on comparison, what we get is this, we have s squared plus omega naught squared and the Laplace transform of x of t, and then this term simply goes to 0 because we have been provided with that condition over here, and then we have minus s, and this condition tells us that x at 0 is equal to x at t is equal to 0 is equal to simply a, which is a constant, so this is s times of a, and that is equal to 0. So now we have the Laplace transform of x at t is equal to, we have SA going to the other side, we can keep a as the constant, and s over s squared plus omega naught squared. And if you remember, we have just obtained the form over here, this is cosine kt. Now instead of k we have the term omega naught over here, so this is nothing but the Laplace transform. We can keep the a outside. This is the Laplace transform of cosine omega naught times of t. We can take the a within the bracket, that doesn't really make a difference, and we have this. So with the Laplace operator on both the sides, we can have x at t is equal to a times cosine omega naught times of t. So this is the solution to the above differential equation obtained by Laplace transform method. Now next we look for the Laplace transform of periodic functions. Now a periodic function is one that is piecewise continuous for some value of time period t which is greater than 0, and it satisfies the following condition, that we look at the periodic function and we have f of t to be a periodic function if it is having the same value over a given period of time. Let us have that time t, capital T in this case, that is the time period. So it keeps on repeating itself at every time period, so from t to t plus 2, t plus t, and t plus 2t, t plus 3t, and it continues like that. So that is the case of a periodic function. Now if we are to consider the Laplace transform of such a periodic function, we proceed as follows. So we have the Laplace transform of f of t, and we know that the f of t is going to extend over the time period t, and it's going to repeat itself in that time period. So we use the general definition of Laplace transform, e raised to the power minus st in the integrand taken from 0 to infinity over the factor t. Now this will lead to, because it's from 0 to infinity, we can extend it from 0 to t for every period. It's not necessarily the time period, but it's the case of the repeating factor or repeating variable in which the function resumes its form. So more or less this can be compared to the time period. Now this is the first first case where we are taking it from 0 to t, then we will be taking it from t over to 2t f of t e raised to the power minus st dt, then plus from 2t over to 3t f of t e raised to the power minus st dt, and it continues right up till infinity. Now let's consider the second term over here. Now for the second term, we have the limits going from t over to 2t. We have the integrand as f of t e raised to the power minus st dt. Now because this is a periodic function, so we can change the limits over here from 0 to t while we make a few changes within that function, where the exponential now has minus of s times of let me write that s clearly for you. So this is a minus of s times of u plus t, where u is any given variable and t is that period over which it is going to have or going to repeat itself. So here the function now changes from f of t to f of u plus t. We can define it as u plus t. Now that taken with the over du, then we can take that st out of it because that's a constant, so e raised to the power minus st can come out, and we have the integration taken from 0 to t e raised to the power minus su, and this is nothing but f of u with the periodic function taken into account times of du. Now u is simply an index which can be changed. So if we change the index, we now have e raised to the power minus, we replace it with the t, so this is f of t and this is dt. So this is nothing but the function itself right from the very beginning. Instead, just we have the limits taken from 0 to t. Similarly, for taking the limit from 2t over to 3t, f of t e raised to the power minus st dt can be given as 0 to t e raised to the power minus 2 times of st. Well, that can stay out of the integration, and here we have e raised to the power minus st f of t dt. So likewise it continues right up to infinity. So substituting all these values that we have obtained in these two cases in that first formula that we have over here, we have on the left hand side the Laplace transform of the periodic function f of t, and that is equal to, we have all the e raised to the power st terms. In the first case it is going to be 1 over here, that is for this one, and then for the second term we are going to have e raised to the power minus st. In the third case we have e raised to the power minus 2 times of st, and it carries on, and the common term over there that is multiplied to all of them is 0 to t, the integration, with the integrand being e raised to the power minus st f of t dt. Now this series that you see, the summation series, that by using the Taylor's series, we have that value to be equal to 1 over 1 minus e raised to the power minus st, and this remains as such. So this is from 0 to t e raised to the power minus st small t f of t dt. So that's the case, or that's the formula for the Laplace transform of a periodic function. Okay, Now we'll use it and see what's the application part of this kind of the application part of this transform. So in one of the questions we have a function f of t, and it is given by this, where f of t is equal to sine t when t is between 0 and pi, while it is equal to 0 when t lies between pi and 2 pi. Now it is extended periodically with period 2 pi. It means it continues or it reappears in its original form at every 2 pi. So we are to find the Laplace transform of f of t of the given function, periodic function. Now the condition that we have over here is f of t is equal to f of t plus 2 pi, and that is equal to f of t plus 4 pi, and at every 2 pi it continues like that. Now the Laplace transform of such a function, as you know, we have just obtained the formula. It is 1 over 1 minus e raised to the power minus 2 times of pi times of s, because it was 1 over 1 minus e raised to the power minus s t, capital T in that case. Here the capital T is equal to 2 pi, so we replace that capital T with 2 pi, and then it is followed by the integration from 0 to, again, the capital T, here that being 2 pi, e raised to the power minus st f of t dt. Now this would have been the case, and this probably would have been the answer in case we had the 0 to infinity in that integration, and that would have had the Laplace transform, but that would have just blown up the left hand side and we wouldn't have achieved a valid result. So that's not to be. This is from 0 to 2 pi, so we have to integrate it, and we have to integrate within the given condition for f of t over here. That is from 0 to pi we have one value, and we have another value from pi over to 2 pi. So we have the term 1 over 1 minus e raised to the power minus 2 pi s, that remains as such. And as for the integration, we have the value 0 to pi and e raised to the power minus st. F of t from 0 to pi takes the form of sine t times of dt in this case, and then from pi over to 2 pi we have e raised to the power minus st, but the function in that case is 0, so the second term goes to 0 all by itself, while the first term is to be integrated. So we have the integration, we'll be doing it in by parts, and by doing that we have the following results. Now we keep the exponential term as the first function and the trigonometric term as the second one, so we get to do the derivative of the second term and the integration of the first function. Now, all that would lead to the final step where we are getting the integrand back again. Now if we are to consider this integrand, that is this one over here, we treat this as simply as I, then we are getting the I back over here. So what that would give us is that we have, let's forget about the 1 over 1 minus e to the power minus 2 pi s over here, and we look at only the bracketed terms. So that integration of, that is the I, that has led us to this entire thing with another I over s squared in the negative term. So what we get from this is that we have I to be equal to, that is the integration that was there in the very first step, actually in the second step, because this term went to 0. So in the second step we were left with only the integration I, and that has led us to the value of I to be this much, and that was multiplied to this factor over here, that is 1 over 1 minus e raised to the power minus 2 pi s. So finally we have the Laplace transform that was to be obtained of the periodic function, that is equal to 1 over 1 minus e raised to the power minus 2 pi s times of 1 plus e raised to the power minus pi s divided by 1 plus s squared. So that's the value of the Laplace transform that we were to determine for the given periodic function by using the concept of the Laplace transform of the periodic function. So after this we proceed to the Laplace transform of the unit step function. Now a unit step function is of the form, we can represent that graphically first. Let me define it first for you. So the unit step function, say u of t minus a, is defined as u of t minus a is equal to 0 when t is less than 0, and it is equal to 1 when t is greater than or equal to a. So that can be represented over here. So we have u t minus a, and this is the value 0. We have the value 1 over here, and this is the point a. So at t greater than a, greater than or equal to a, it will have a value 1, and before that, from 0 to a, it has a value 0 for t less than 0. So a is greater than or equal to 0, of course. So with this definition of unit function, let's express a given function in terms of the unit step function and find its Laplace transform. So we have the function which is of the form that f of t is equal to 8 when t is less than 2, and it is equal to 6 when t is greater than 2. Now as a solution of it, what we can do is we have f of t, now that 8 and 6, that can be represented as follows. If we have 8 plus 0 instead of 8, and we have 8 minus 2 instead of 6, then it remains as such, and we can take that 8 plus 0 and minus 2 are kept in that condition, and we can take a minus 2 common term to be out of it. So 8 plus of minus 2 times of, this is 0, this is 1, and this is when t is less than 2, and this is when t is greater than 2 as per the condition. Now that is a unit step function that we just obtained. So this is minus 2 times of u of t minus 2, because it's in the same form as the unit function. So this minus 2, this plus can be taken out, so we take out that plus term over here and replace it with completely with that minus sign. So 8 minus 2u times of of t minus 2. Now the Laplace transform would be, for the left hand side we have Laplace transform of f of t, that is equal to 8 times the Laplace transform of 1, because that is 8 into 1, and then we have minus 2 times of the Laplace transform of the step function, which is u of t minus 2. We'll get back to that Laplace transform of the unit step function. The first term, however, is absolutely straightforward, where we have 8 over s, because Laplace transform of 1 is going to be 1 over s. We have proved that right in the first video. And in the second case we have a minus 2 and the Laplace transform of step function. Now before writing that, we will see what the Laplace transform of the unit function provides us. So let me do that over here. Now the Laplace transform of the unit function, let us say it is t minus a over here, that is going to be equal to 0 to infinity e raised to the power minus st u of t minus a times of dt. That's by definition. And if we set the limits, that is from 0 to infinity, first up we take it from 0 to a, where the given function is 0. So this is going to be 0, because within that 0 to a, as you can see right at the top, that function does not exist. So that is 0 over there. And then we are going to integrate it from a over to infinity, and we are going to have the value over there is simply 1. In that case the value is 1. So this is e raised to the power minus st times of 1 times of dt, and that is going to be in that limit from a to infinity. What we are going to get is simply equal to, I'll extend this over here, this is going to be e raised to the power minus st over minus s. So this is e raised to the power minus as, because of the lower limit over there, divided by s. You can integrate that within that given limit and you will obtain this result. So in this case, a being equal to 2, we have this value over here to be equal to e raised to the power minus 2s over s. So this is the value of the Laplace transform of the function of the unit step function over there. The given function was first of all obtained in terms of the unit step function, and then we had the Laplace transform of the unit step function as well. Now there is one more thing that I would like to provide you information about, is that if we were to represent this kind of a unit function graphically, that is u of t minus a minus u of t minus b, which means the unit step function will have a value 1 above the value of t greater than or equal to a, and less than the value t greater than or equal to b, less in the region, in that region, that is t greater than or equal to a and t less than or equal to b, there the value is going to be 1, and the rest of the places the value is going to be 0. So that is how we define this kind of a function, where the unit function is having the value 1 within that range from a to b. We will be continuing with some more numericals on the Laplace transform, the unit step function, and many more applications of the Laplace transform in the upcoming videos. Till then, thank you for watching.